Thanks. It's my absolute pleasure to have Jan present here. It's not his first time. It's not his first rodeo, as they might say in Texas. But Jan actually embodies sort of this micro economist slash econometrician, and he's an absolute wizard in Stata. So we're just absolutely thrilled to have him present. So take it away, Jan.
Well, I can start without the slides because the slides are not right. So the slides are not that important, at least in the very beginning of my talk. The first slide is titled, "What am I doing here?" And what I'm usually doing at Stata conferences is that I find something during my work that is annoying me enough to put together a presentation about it and then complain about it in front of the Stata developers. And that's what happened last time I presented at the Stata conference. What happened last time was that I was working with these massive data sets, hundreds of millions of observations, and I was doing a lot of visual analyses, producing charts. And I realized that the charts are just really slow to produce. I could have kind of calculated all the things that I wanted to be plotted in a fraction of the time that it took the chart to materialize in Stata. And I just couldn't wrap my head around it. What was going on? So I looked into the Hadoop files, and I realized that what Stata is doing behind the scenes is that in order to produce the chart, Stata saves the entire dataset to the disk and then clears it from the memory and then loads the data which is supposed to be charted. And then it restores the dataset back to the memory. And that is kind of the workflow, right? And as long as your dataset is small, that's kind of okay. That's not a problem because the preserving and restoring of the datasets is a pretty fast operation. But if your data set is, 10 gigabytes or more, and you are trying to do this quickly, well, then that's going to take you a while. So I was not very happy about that functionality, and I came up with a solution which boiled down to the use of frames, this very nice functionality where you can store multiple data sets in memory at the same time. And I produced a little package which kind of created charts for high dimensional data, or at least big numbers of observations by using the frames, so that I would be kind of bypassing this preserving and restoring. And that package works really well. I encourage you to try it. It's called Plot Tabs. And it also operationalizes some functionalities that I was missing from the traditional Stata commands. Here we go. So we might have the presentation on soon. But to be honest, the package itself was just a proof of concept. It was intended for Stata to kind of take it and run with it, right? Because there's no obvious reason why you shouldn't incorporate it into two-way and histogram and all the other charting tools, right? The preserving and restoring is just a legacy. It's a legacy issue, which wasn't an issue in the earlier versions of the software, but right now it's just redundant and it's making our lives a little bit difficult. Okay, so I'm still waiting for that feature to be implemented. I'm keeping my fingers crossed for Stata 19, but let's see. Just putting it out there. All right. Wonderful. Okay. All right. So starting again, hello, welcome to my presentation. This was my first slide. This was what I just talked about. I grumble about features of Stata, and I try to identify the stuff that doesn't work, and I also try to propose solutions. The solution for the graphing problem is this package, the SSC install plot tabs. And today I want to highlight another issue and also propose a solution for this issue. Okay, now the title is extremely boring, and I understand that this might not be for everybody, but think about this as a murder mystery, okay? Imagine that you are on in the carriage of an Orient Express, and there has been a murder. And so I'll try to do my best to impersonate Hercule Poirot, although I'm not going to do the accent, so don't worry about that. So let's talk about the murder, all right? Yes. So the murder entails a very simple arithmetic operation. And just to set a scene, here's a very rudimentary Stata code, which creates a data set with 10 observations. And we populate this data set with one variable, x, which is calculated by taking the n, the order of the variable, and dividing it by 10, right? And then we list this x variable. And this is what happens. We produce a list with 10 elements. Pretty straightforward, right? No black magic. Now, let's introduce a little bit more conditionality into this exercise. So now what we will be doing, we will be listing, once again, the x, but now with the condition that x should be smaller or equal than 0.4. Now, what do you think is going to happen? We should be listing the first 4 observations of the data set, right? Right? So here's what happens. We're not listing the first 4 observations of the data set. We're listing only the first 3. And that's very weird. So this is my murder. There's some strange thing happening in Stata. And I was just trying to understand what the hell is going on. Okay. Now, the gray hairs in the audience might remember something called the floating point precision issues. And at this point, you might be starting to get flashbacks of PTSD from the early years of computing, because floating point precision was a big problem in the early days. And the issue is that computers do not really know very well how to deal with non-integer numbers, like fractions, like pi, basically anything that can be counted on your hand, right? So this is an example. 1/3 can be approximated as 0.333333333 until infinity. But the computer can't really store this number. We can't go until infinity. We have to resort to some approximation, right? And that's what we do. We approximate the numbers to some finite degree of precision. And Stata does this too. So if you print sufficiently long number of decimals, this is exactly what is going to happen, right? It's going to be correct up to a certain length of the decimal numbers. And all of a sudden, it starts going a little bit random. Okay. This was a major issue in the early days of computing, because this element indeed used to be random. And therefore, if you calculate the same number twice, then you would have these different ending elements, which means that you couldn't really evaluate any equality conditions, because the numbers would never be exactly the same. Now, we have moved from that, and right now, the exact sequence of numbers, which is outside the precision range, is standardized. So we can replicate the same number multiple times, no matter how many times we define something to be equal to 1/3. The nice thing is that this is replicable across programming languages, such as Stata and R. So if I create 0.3 in Stata, it's going to be the same as 0.3 in R. Oh, sorry, 0.3333, 1/3, 1/3. The issue arises if you start doing the same operation across different computer architectures. And you might remember from Luis's presentation earlier on that he said that sometimes on Windows and Macs, the numbers will not exactly coincide. And that's exactly this problem. That's the very same concept, right? So these kind of ending sequences might be kind of computer architecture specific. But at least we can know that on the same machine, even across different softwares, different programs, we should be getting the same numbers. And that's really important for the sake of replicability. Okay, so let's go back to the example and ask what happens with 0.4. Let's look at how Stata handles the precision of 0.4. All right, this is interesting. So now we can see that the number that is stored is actually greater than 0.4. All right, so we have this residual term, which is slightly larger. And you might be thinking, well, that's it. That's the murder. That's a murderer. This number is greater than 0.4, and that's why 0.4 was excluded from the list of the numbers in the conditional statement, right? Makes sense. Unfortunately, it doesn't. It doesn't make sense. Because, well, first of all, if it did make sense, then we should be able to replicate exactly the same behavior across software packages. We should be able to replicate this in Python, in R, whatever, right? So let's try to do this. Let's try to do this in R and see what happens. So this is a workflow which is basically equivalent to the Stata code that I showed you before. Once again, 10 elements, and we will list the elements from a vector which are smaller or equal to 0.4. What happens? 0.1, 0.2, 0.3, and 0.4. R achieves the correct solution. So that means that the floating point arithmetic in and on itself is not the murderer here. That's not why we are seeing this issue. And that really makes sense because I mean, the computer is really evaluating the two identical numbers. You know, both of them should be approximated to the same degree of precision. And as we have established, these numbers are standardized, right? So what we are basically doing is we are comparing, or we are asking whether this first number is smaller or equal than the same number, right? We are using the same standardization, the same approximation, the same precision. So this can't be the reason. This can't be the culprit. And when I first raised this on social media, people were saying, "Well, this is just floating point arithmetic. This is just an unnecessary evil for us to kind of deal with. That this is just part of how software is." But it's really not. The floating point arithmetic is not the reason why this is different. So what is going on? Yes. Yeah. I mean, it's a murder mystery. There must be a resolution, right? There must be a resolution. Otherwise, I would be a bad detective. Okay. So now we are getting to the unveiling, to the Scooby-Doo moment, right? We are looking at under the mask. That's right, and the dog. Okay, so what is going on in Stata? Well, the Stata, as the title of my presentation implies, is storage types. That Stata uses different storage types for numbers. Okay, so if we are storing the numbers in a data set, then Stata is by default using single precision. Whereas if we are doing arithmetic operations on whatever data, we are using double precision, more precise numbers. Sometimes we are even using quad precision, depending on which command you're using, but this is the default, right? And that is a problem because let me show you what happens if I print out these long strings of decimals for the number that is used for the arithmetic operations, which is stored in double precision, and the number which is stored in the data set, which is in single precision, right? Single precision is a less reliable indicator of the actual number because the exact portion ends earlier. The double precision is much more precise, right? But now we know the villain of the story, right? Because when we were listing uh, these first four values, or three values actually, we were comparing the number that is stored to this number, and we were asking whether this number is smaller or equal to this number, and it's not. It's bigger. I mean, it's clear from here, right? Um, and that's a problem. Yeah. So we can actually force theta to produce the right result, the right behavior. If we force the number that is used for the arithmetic operation to be also single precision. Okay, so that's exactly what I've been doing here. I still have the variable stored as single precision, but now I'm comparing it to a single precision 0.4, not the double precision 0.4. And if I do that, then I get the behavior from R. We are comparing two identical numbers because of the standard, right? So this is the correct result. Now, you might be asking yourself, so what? I mean, these things happen. You're talking about minuscule changes along the margins. Why bother with this? And Stata Manual will agree with you. But this is what Stata says, right? This is not a problem because the calculations are done in the more precise storage type so that we shouldn't have any issues with kind of arriving to the correct result. But I tend to disagree. I mean, that's why I'm standing here in front of you, right? We've been talking about causal methods for quite a while today, and these mismatched precisions can be very damaging in the context of causal estimation. And just to give you an example of what I'm talking about, let's look at the regression discontinuity designs. Now, you might not be aware of this method, but it's kind of the bread and butter of causal inference, right? We have some processes which are divided by a discontinuity where the outcome value jumps discretely to some new optimum, right? And basically, this difference between the two lines will tell you the causal effect of whatever you are studying. And that's great as long as the values surrounding this discontinuity are measured precisely and assigned correctly to the left or right, right? Both of these charts are taken from journal articles. One of them was written by a Nobel Prize laureate, but they were written in Stata under this kind of differing storage type issue kind of underlying the software. So we can't be sure that these values are really assigned correctly. And here it's not too much of a problem, but here this could play a major role, right? Because if you would shift them to the right, maybe the difference between these two lines would become statistically significant, and that could overturn the findings of the study. Okay. So personally, I think that this is extremely important. I can, well, I can tell you that this is not the issue here. I've checked the code and the code runs correctly. But in principle, this is a problem and it's an unexpected behavior on the side of the analyst, which we just have no idea of verifying or knowing how to verify. So I don't like that. Um, Also, I mean, you can still think of the first graph and say, well, okay, here it wouldn't really make a difference in terms of the statistical significance. But if you're comparing multiple programs, then you can have wrong ordering of their relative usefulness, right? Just because the software has assigned the wrong people to the wrong side of the discontinuity. So that's a problem. And yeah, I think that this should be addressed. Especially if we are concerned about replicability, and I hope that today's workshop has demonstrated that we are concerned and we should be really pushing for replicability in science. We should really endeavor to eliminate these unexpected and potentially damaging behaviors, especially if the solutions are readily available. And fortunately, they are. So let's talk about solutions. Solution number one, everything in double. Just make sure that Stata computes everything in the double precision, right? So I would love to see Stata move away from the single precision default for storage to the double precision, because that would be best, right? You do not have to tell anybody, the practitioners. You just kind of flag it as one of the changes, and then people kind of moving forward might struggle with replicating some of the initial findings, but then again, at least they are getting to the truth. Exactly. Yes. So that would be my solution, especially since the only disadvantage of this solution is that the data sets will become slightly bigger. Because right now we are storing in single precision, which means that this is a rather economical way of storing variables. But I mean, modern hardware just we don't have to do this to ourselves, right? We have hard drives of hundreds of gigabytes or terabytes, so just kind of adding a little bit more precision to the non-integer variables is not going to be a make or break issue. I think it's really a legacy issue by now. For what it's worth, R uses exactly the same default. The stored variables in data frames and the numbers that are used for arithmetic operations are both in double precision. Okay, so once again, you're ensuring that the code is going to be replicable across platforms, and that's really important. In the meantime, if you want to be safe, you can just set the double precision standard manually, right? This is the easy solution as long as you are aware that there's a problem to start with. So you can set type to double and everything is going to work out, but you can't set type to float and expect the arithmetic to be in single precision. That's not going to happen. The double precision arithmetic will override this operation, and your data and your analyses can be still potentially done wrongly. Okay, Chuck.
Sure, I understand. What if I type generate double x equals divided by 2? You're saying the arithmetic is still done in single precision? Is that what you're saying? Even if I type generate double, it's stored in double. The arithmetic is done in single precision.
So arithmetic is always done in double precision. Okay. You could address this on a case-by-case basis by doing generate double, and then you would get, once again, the correct solution, right? But you would have to make sure that you specify the correct storage type every time you define a non-integer variable. Okay. Solution number two is smart precision handling. This might be something to consider as well, especially if you're kind of alternating between different precision types for different operations. If some operations are handled in quad precision and some operations are handled in double precisions, then you can do something like this, right? I mean, this is a pseudocode which basically checks for the type of the variable that is being evaluated against the conditional statement, and assigns the correct precision type to the arithmetic operator based on this cross check, right? This requires a little bit more machinery to operationalize, And in principle, it can also run into problems if the conditional statements become really complex. But it can be also a solution. The advantage of it is that it would avoid making the data sets larger by default, and potentially also, allow for this quad precision handling to be done. So yeah, these are my two solutions. I have to make a disclaimer. I do not know, the guts of Stata terribly well, and maybe there's some hidden reason why the single precision default for storage is actually preferable. I don't know whether this is the case, and I'm happy to be convinced that this is the best of the two worlds that I'm proposing. But unless this is the case, I would suggest that we move on and we try to make conditional statements using the same storage types as the data. And I think that the first solution is the most straightforward to implement. So I hope that this message resonates. Now, I think that the Stata practitioners will thank you for it, or they would if they even knew that there was the problem to start with. Okay, so just kind of making sure that we are not making mistakes by ignorance, this seems to be a good way forward. And let me leave it at that, and thank you for your attention. Cheers.